won't be here. Not if I'm sick. Apparently I look sick. And not in like the cool, like, oh, you look sick, bro, way. Like, you look sick, like, you look pale. Yeah.
You look like you're gonna die.
You look like death. Okay, so we are on chapter 11, the steady state frequency domain analysis chapter. So this is the last chapter of the dynamic systems notes, okay? And let's kind of back up and let's just like talk about what this chapter is about before we get into this specific lecture. So this chapter is going to be about the frequency domain, okay? So we are going to develop some very specific tools. Sorry, I don't have my notes. There we go. We're going to develop some very specific tools for analyzing systems in the frequency domain. But I also want to make sure that we stay focused on the fact that the frequency domain concept is actually the most important aspect of this. Are these going to help? Okay, good. We know. we tried them. So the frequency domain is a very important concept, and we really need to make sure that we don't get lost in the tools and thinking about this technique or that technique. And so hopefully, I mean, this is one of the most important concepts to come out of this course, so hopefully that's something that you guys get in the coming weeks. Also, I will mention as a caveat that this is not, like this frequency domain analysis is not ineffective for transient analysis as well. But steady state analysis is what we're going to be focused on. And we will introduce some tools that along the way I'll say, oh, so you could do this if you wanted to find the total response or the transient response. And I'll mention those as we go. But we're not going to be doing a lot of transient response discussion. So that's why I say steady. We could do another chapter on the transient aspect. And so I'm kind of focusing on the steady aspect. Okay, so without further ado, let's start lecture 11.1, Fourier series. Fourier series are mathematical series that can represent a periodic signal as a sum of sinusoids at different amplitudes and frequencies. And that's kind of like the whole thing, but like there are details. Okay, but like that first sentence kind of gives it the whole thing away. So they are useful for solving for the response of a system to periodic inputs. Okay, so that's what we're going to be using them for in this chapter. That's one of the main things. However, they are probably most important conceptually. They are our gateway to thinking of signals in the frequency domain. That is, as functions of frequency, not time. Okay, and that's where we like really need to be focused, I think. To represent a function as a Fourier series is to analyze it. We say it's to analyze the function as a sum of sinusoids at different frequencies, omega n, and amplitudes an. So sub n here does not mean natural frequency. It's an index. Unfortunately, n is the like standard notation for Fourier series stuff. And I've heard that you guys already have seen Fourier series, so I'm not going to spend too much time talking about Fourier series, but we are going to do an example today and all that. But this is the standard notation. The frequency sub n and the amplitude sub n. So these are multiple frequencies and multiple amplitudes. So the sinusoid at a given frequency has a given amplitude. That's what we're discussing. Its frequency spectrum is the functional representation of amplitudes an versus frequency omega n. So that's like high level. We're thinking, now let's get into specifics. How do we actually define these quantities? So let's begin with the definition. This is the trigonometric form. We're going to also do the complex form in a moment. So the Fourier analysis of a periodic function y of t is, for positive integers including 0, period t, and angular frequency omega sub n, where n is an integer. We have these two equations, an and bn. They're integrals over one period of the periodic function y, and we put that function in there. So we're going to analyze the function by putting it into these integrals, okay, and getting all of these an's and bn's out. One that corresponds to cosines and one that corresponds to sines. Now, so when we do the analysis, what we're doing is we're finding a bunch of these coefficients, these components. And you might think, well, what good are those components? What do they represent? Turning it around and looking at the Fourier synthesis helps us to begin to understand that. And when we start to think about the spectrum, it'll help us understand what those ANs and BNs are even more. But we're not quite there yet. It'll get more motivated. The first way that we motivate it, though, is to do this next part. So the Fourier synthesis of a periodic function y of t with analysis components an and bn corresponding to omega n is the sum from n equals 1 to infinity of all these an's times cosine omega n t's and plus all the bn sine omega n t's. So this is, for just a given n, this is just a sinusoid, right, at a given frequency and amplitude. The amplitude is the root sum square of an and bn, right, if we were to use that trigonometric formula that we have used in the past. I call them like the 2-to-1 formulas. We want to use those. Then the amplitude of this sinusoid is the square root of an squared plus bn squared, and then the phase is the arctangent of bn over an or whatever. So we have a sinusoid at each frequency and an amplitude at those for each sinusoid, okay? And that's what we do with the synthesis. Is we take those components that we found from the analysis, and we can reconstruct the signal with them. And then there's this term here, which is called the zero frequency. Or DC amplitude when n equals 0. So that's the trigonometric form. Is that the form that you guys have seen in the past with the trig functions in there? That's usually the more common one to introduce. Let's consider the complex form of the Fourier series, which is analogous. So in the complex form, we're going to use Euler's formula, Euler's identity, to say, oh, okay, instead of writing things in sine and cosine, we're going to write things with e to the j theta, right? That's the complex sinusoid form, the imaginary sinusoid specifically. So the Fourier analysis of a periodic function y of t is, for n being a positive, including 0 integer, period t, and angular frequency omega n equals 2 pi n over t. So it's integer multiples of 2 pi over t. We have these little c amplitude coefficients. And these ones, there's plus and minus c, so there's like c negative 1, c negative 2, and there's c positive 1, c positive 2. And they are defined by this integral given here, in which we once again place the function, the periodic function that we are analyzing, that we're taking the Fourier series analysis of. And then we have this e to the minus j omega n t term, which is the sinusoid, okay? But it's a complex sinusoid. It's got a sine and a cosine kind of built into it. So you can kind of pack them into one term. Now, mathematically, this form is much easier to work with, okay? Because I don't know if you guys have done a lot of integrating, but when you integrate with sines and cosines, it gets a little bit messy often. When you integrate with an exponential, it tends to be nicer. That's one reason why working with the complex form is nicer. There are some other nice mathematical things that pop out too. Also notice you only have to compute 1 instead of having to compute 2. So we like that usually. I mean, maybe you guys like computing 2 better than 1. I don't know. I'm not here to judge. You know, it's up to you. You guys can decide. You guys want to do more? It's kind of cool too.
I like that bird in the hand versus bird in the bush.
Yeah. 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 I mean, that is a saying. Yeah. So yes, it is a saying.
That has imaginary ones, right?
Mm-hmm. It is. Yeah. It's 6 in one, half dozen in the other. The Fourier synthesis of a periodic function y of t with analysis component Cn corresponding to omega n is, so same thing, we decomposed the original function through the analysis, and now we're going to reconstitute it in the synthesis by summing up all of the amplitudes with these sinusoids, but complex representation of sinusoids. And that's the synthesis. So it's pretty it's equivalent, right? So you could do either one. They're both equivalent. So it's important to keep that in mind. And in a moment, we'll talk about how to convert. So we call the integer n a harmonic. So that terminology is going to come up a lot. Harmonic, okay? A harmonic. And you may have learned that term, hopefully, in physics. A harmonic. Same exact thing. They're using it the same way that we're using it. And the frequency associated with it, omega n equals some integer multiple of the frequency 2 pi over the period, the harmonic frequency. Okay, so we call this frequency the harmonic frequency. We call the integer n the harmonic. So we could say like the fourth harmonic is n equals 4, right? And the fourth harmonic frequency is omega 4 equals 2 pi times 4 over t. That's the fourth harmonic frequency. Cool. There's a special name for the first harmonic, n equals 1. It's called the fundamental frequency. So when n equals 1, we get omega 1 equals 2 pi over t. It's the period of the original function, too, right? Of the function that we're analyzing. It is called this because all other frequency components are integer multiples of it. So n equals 2, n equals 3, n equals 4. We're integer multiplying this fundamental frequency. Cool. So these are a lot of terms. I mean, there's a lot of terminology in this lecture, and I know that sometimes, like, when a lot of terminology comes at you, it's like, woo, it's too much. Like, I'm not getting all the terminology. But this is terminology that is going to stay with us. It's very important terminology. You're going to hear it throughout your upper level classes, and so it's important to keep this terminology straight. And this lecture I think provides a pretty good place to come back to like remember what that meant exactly, because it's got all of the definitions in there pretty much. It is also possible to convert between the two representations above, so the trig and the complex form. So the complex Fourier analysis of a periodic function y of t is for the ANs and BNs above. So if you have a trigonometric form and you want to go to the complex form, this is how you do the conversion. And if you have a complex form and you want to find the trigonometric form, this is the conversion. Okay? So you can go back and forth. So you could do the analysis in the trig form, or you could do the analysis in the complex form, and then you can convert if you want. So, cool beans. The harmonic amplitude is this. So we use big C here. Big C sub n is equal to the square root of an squared plus bn squared. So that's the trig form, if we have the trig form of the coefficients, of the components. And that is just the amplitude of the single sinusoid. If you were going to combine, like I said up here, if you're going to combine your cosine and your sine together, which you can do, there's a trig identity that lets you do that, the single sinusoid that would result would have amplitude square root of an squared plus bn squared. So we call that down here, we define it as being the harmonic amplitude C sub n. So we have a harmonic n, a harmonic frequency, which omega n, and then the harmonic amplitude is capital C sub n. And if you have the complex form, this is how you do the conversion to the harmonic amplitude. Cool. A line spectrum is a graph of the harmonic amplitudes as a function of the harmonic frequencies. Okay? And the line spectrum is where we start to really get into like frequency domain thinking. Okay? So the following illustration demonstrates how sinusoidal components sum to represent a square wave. A line spectrum is also shown. So let's take a few minutes and just really dig into this graph, this representation. There's a lot going on here. Let's start out in the time domain, okay? So we have this axis, this time axis. And this time axis has amplitude plotted through time. It looks kind of like a square wave. It's a partial square wave. And we'll talk about why it's not a full square wave representation in a moment. But you have this sort of square wave in time, right? And what we're interested to do is we're interested to do a Fourier analysis on this time domain signal. This over here would be called the time domain. Thinking about the signal through time. And then what we're going to do is we're going to say, okay, we do a Fourier series analysis on this time domain signal, this square wave, and we compute our C's. So actually, what this first one is C was actually, so the frequency is omega 1. This frequency corresponds to omega, it's actually 3, and I'll explain why we're skipping 1 in a few minutes. It turns out the omega 2, the omega 4, all of the even ones end up having 0 amplitude, so we're skipping them in this graph. Omega 5, omega 7, omega 9, omega 11. Okay, so those are the different frequencies, and we're computing our ANs and BNs or little CNs, and then we're computing our harmonic amplitude, big CN, okay? And that harmonic amplitude multiplied by the sine at that frequency omega 1 of t is what's represented here in light blue through time. So a sinusoid is pretty boring, really. I mean, it just repeats itself over and over again, right? So what we've got is this sine wave that is at the amplitude Cn. So I'll try to like put in like a height marker here. I'll say this is C1, this is C2, 3, etc., the heights of those. But we don't really need to plot them through time. It's just like showing a lot of squiggles for no real important reason. We already know what their frequency is, so like why? Like we don't really need to have this whole thing. So what we do instead is we kind of collapse this whole plot. So we smush this thing, and what results is this spectral amplitude plot over here. So this is the line spectrum. And what we plot is, so for omega 1, omega 3, omega 4, or 5, omega 7, omega 9, omega 11, we plot just what the amplitude is. We know what the frequency is. It's omega 1, omega 2, whatever. And the amplitude is just going to be C1, C3, C5, C7, C9, C11. And there are even ones in between there. It just turns out in this problem they're all 0. So that's why they're not shown. But we could show, like, there is our C2 and our omega 2. It just so happens that these ones are all 0. So I'll put them in there as just dots. So that's our line spectrum. And that's like the first way that we can start to really have access to thinking in the frequency domain. Because that means this square wave time domain signal has a spectral amplitude. It has this spectrum or line spectrum that falls off as frequency increases. It has a large component at the fundamental frequency, right? That's where the biggest amplitude comes in. And then the amplitude decreases from there. So later on, not too much later on, probably when we come back from spring break though, we'll be talking about how a system will respond to certain frequencies and not respond to other frequencies. And so if your input signal has a certain spectrum and your system has sensitivity at certain frequencies versus other frequencies, we'll be able to understand how the system will respond to that input much better. Or maybe there's for some reason you don't want certain frequencies to come through in your system, which is very common. We want our system to sort of filter out different frequencies. And that's something that we'll discuss as well. So this is like, we're just getting to see the very beginnings of a very exciting world of frequency domain analysis. Yeah?
So when you say it's not going to respond to certain frequencies, do you mean that nothing happens, or do you mean it's not what you want?
So there can be some frequencies that are sort of like dead zone frequencies where it literally won't transmit anything through at that frequency. That's more rare. Usually there's a system will have more frequently it'll have less response at the given frequencies. It'll be kind of like I don't want to take the analogy too far, but have you ever dribbled a basketball on an old wood basketball court, and there are like those spots that just kind of like the ball just doesn't come back up to you very well? Those like dead zone spots on the court. That's kind of how you can think of some of those frequencies where like the ball will bounce, but like not as much at those frequencies. Or so that frequency, not a lot happens if you excite the system at that frequency. And then there are some frequencies like near the natural frequency, near resonance is what we would say, where the system responds a lot and has a lot of excitement from a smaller input. So we're going to start thinking about systems in those terms. It's like what frequencies do they respond to? Which frequencies do they filter out or reduce significantly on the output? And this thinking in terms of the line spectrum and the frequency domain is going to help us do just that. And if anybody's into music's a pretty popular thing. So like some folks that are into music out there, there's a lot of the stuff. There's a lot of music theory that is related to this, and a friend of mine. I'm a very amateurish electronic musician, very amateurish. He's like a legit electronic musician. When he was first showing me his software, like they put on filters. So like maybe I'll do a demo for you guys someday where you put on a filter on the signal and it distorts the signal, right? It just like auto-tune is an extreme kind of example of that. But yeah, I mean, like you can do all kinds of filtering, where and you can also just straight up like do like specific amplification and distortion. But like your audio filtering is exactly the analog that we want to think of in terms of like what our systems do too. So you take an input and you change it and you distort it, and that's what our systems do to inputs as well. So if that's a useful concept for you, I encourage you to use it. It is the correct way of thinking about it. So, and he like showed me what we'll come to know as being a Boda plot, and like he was like shaping it for like the filter, and I was like, I completely understand what you're doing. Like this is amazing. I love this. It was great. All right, cool. So I think that we got that, and so like this is a very useful representation. I would encourage you to return to this and like make sure this is really concrete for you. So let's actually use this as an example. So let's compute the associated spectral components in the following example. So we want to know what C1, C2, C1, C2, C3, 4, 5, all of these are. We want to know what the frequencies are and what the amplitudes are. So we could construct a line spectrum. So compute the first 5 harmonic amplitudes that represent the line spectrum for a square wave in the figure above. We weren't given an amplitude, so let's assume that we have an amplitude of 1. So assume a square wave amplitude of 1. So let's draw a little picture in the margin here. What does a square wave of amplitude 1 look like? And we see it up there, but let's draw a little bit more precise version. We've got the one that was shown up here is an odd one, so let's use the odd one. You can also make even ones or ones that are neither even nor odd. But this is the one that's shown on the other figure, so let's just continue with that. So this has amplitude 1. It has period t, so this would be t over 2, time equals t over 2. This would be t over 2, negative t over 2. And of course, we're plotting this through time. So we want to compute our spectrum. It doesn't say if you want to do it trigonometric form or complex form, but in my notes I did trigonometric, so I'm recommending that. Let's do that. So let's compute an. So an, for just from the definition above, it's the integral. Remember, we can actually integrate over any period. It doesn't have to be negative t over 2 to t over 2, but oftentimes that's a good one. Sometimes you choosing 0 to t is easier. Sometimes choosing something else is easier. So it's up to you. I think that in this case, integrating from negative t over 2 to t over 2 makes sense because this is a piecewise continuous function, right? And the two piecewise, if you go from negative t over 2 to t over 2, there are only two different piecewise definitions in those two intervals, so it's pretty straightforward. So let's also put in y of t. So y of t is just this function, right? The square wave. And then the an one is the cosine one. 2 pi n little t over big T dt. And if we break this up into two integrals over the interval negative t over 2 to 0 and then 0 to positive t over 2, we have nice constant values of y of t. So then we can just plug in negative 1 for this interval and positive 1 for this interval, and we are good to go. So let's pull the negative sign out front. We're going to put negative 1 in here, so we'll just pull it out. From negative t over 2 to 0, y of t is negative 1. We already pulled the negative 1 out. Cosine 2 pi n little t over big T dt plus t over 2 integral from 0 to t over 2 of positive 1. It's positive 1 in that interval, y of t is. So cosine of 2 pi n little t over big T dt. All right, so now let's think about this for a minute. Cosine is an even function, right? Both of these integrands are the same, right? Cosine of that. It's not hard to compute the integral here, right? Like it's an easy integral, but we don't even need to. We can just argue our way to what the answer is going to be here. And it's irrelevant of what that integral actually is. So if you have an even function, cosine being one of them, I did not switch over to green somehow, and you integrate from negative anything, so if you integrate from negative x to positive x, the integral from negative x to 0 is equal to the integral from 0 to x. It's symmetric, right? So this area here equals that area there every time. So these are going to be equal to each other. These two integrals will be equal to each other. Those two integrals are equal to each other, and their coefficients here are equal to each other, but with opposite sign. What will this be equal to? 0. Good. So here's something that I'm not going to derive for you, but is always true. If table. Yeah, see table. We're going to make a table. So this actually happens every time. I set us up. Like I knew that was going to be 0, but I set us up. I know. I'm sorry. I apologize. So let's make a little table. Y of t is one column, an is one column, and bn is one column. If y of t is an odd function, like our y of t was an odd function, then an is always going to be 0. And bn you have to compute. If you have an even function, then an has to be computed, and then bn is always 0. So that's a nice little shortcut if you remember it. If you don't remember it, no big deal. You just have to do the integral and you find out it's 0. Oh yeah, I forgot. It was even or it was odd. I knew that had to happen. So there you go. Now, Bn hopefully is not 0 everywhere, or we have screwed up somewhere. So let's compute Bn. From the definition, it's 2 over t, integral from negative t over 2 to t over 2 of y of t, the square wave, times sine of 2 pi n little t over big T dt. Once again, we can split this at time equal to 0. So we'll do two integrals, negative t, 2 over t, integral from negative t over 2 to 0. Once again, y of t was negative 1, and we pulled the negative sign out, of sine of 2 pi n little t over big T dt, plus 2 over t, integral from 0 to t over 2, sine of 2 pi n little t over big T dt. Okay, so this time we don't have that same situation because these integrals actually are equal but have opposite signs. So what we end up with here is it's pretty easy to compute the integral, each integral. And we end up with 2 over n pi times 1 minus cosine of n pi, which is one way to represent Bn. Another way to represent this is to say, well, we have this integer n in here, and when n is even and when n is odd, different things happen. So let's see what that looks like. So if n is even, we're going to have something, and if n is odd, we're going to have something else. So if n is even, that is, so n equals 0 is an even number, right? So 0 is an even number. I don't know if that's something that surprises you, but it is. I know. So cosine of 0 is 1. 1 minus 1 is 0. 0 times 2 over n pi is 0. If you put in 2, so that's the next even number, increasing it. Cosine of 2 pi is 1. 1 minus 1 is 0, etc. So this is always 0 if n is even. And if n is odd, then cosine of pi is negative 1, right? So we're going to get 1 minus negative 1, or 1 plus 1. 2 times 2 is 4 over n pi. And that's true also for 4 pi, 6 pi, all of the even ones. So that is our Bn. And finally, we just need to compute the harmonic amplitudes. So the equation is C sub n equals the square root of an squared plus bn squared. C of 0 is equal to, it's an even number, so bn is 0, an is 0, so it comes out to be 0. C1, an's always 0, bn is whatever this is. Well, what is this always going to be in our case? An's always 0, so we get the square root of bn squared. So what is it? Yeah, absolute value of bn, because bn can be negative. So absolute value of bn. And bn actually in our problem is never negative. This is always positive. So we don't really need to take the absolute value, but in general that's what that is. So we have 4 over 1 pi. So 4 over pi. C2 is even, so 0. C3 is odd, so we have 4 over 3 pi. C4 is even, so 0. And C5 is 4 over 5 pi. Great. So those are the first, well, these are the first 5, I guess. The DC one usually we leave off. We don't count it as a harmonic, but yeah. Okay, so that's that. Those are the values. So that's what we just computed what the heights of these are. So we could plot it in 2D. So let's do that. Just we have a minute, so let's just go ahead and do that. So we've got omega frequency domain. We've got spectral amplitude. And we've got 0 here. We've got 1, 2, 3, 4, 5. So our omega 1, omega 2, omega 3, omega 4, omega 5. And let's go ahead and get a nice color. Oh, you want teal? I'll go with that one. I really like that blue. Omega 1 was C1, right? Which is like 4 over pi. And, oh, I forgot that omega, that C0 is 0, right? C0. Omega 2, C1 equals 0. Omega 3, it's like a third of the height. So that's C3 equals 4 over 3 pi. Whoa. 3 pi. Omega 4 is 0, and omega 5 is C4 equals, or C5. C5 equals 4 over 5 pi, and then C6 would be 0, and you could just keep going. This follows a like 1 over omega shape, essentially 1 over x sort of fall off.
Is it like always?
No. And in fact, so the shape that this is like unique for every different function. Like a sawtooth is going to have something that's weird, and they don't always decrease either monotonically. So like sometimes like the first one's small and the second one's big, and yeah, so it kind of it depends on the function. And this is like the shape of the function is something that we're going to get into in the Fourier transform in the next lecture. And the Fourier transform is actually it's got functional shapes to it that are, I guess, easier to think about than the line spectra, I guess, the envelope shapes. All right, we will pick this up on Friday. I'll see you guys then.